Welcome to this deep dive. Today we're exploring a really fascinating tool that sits right at the intersection of mathematics and statistics.
Indeed. It's a technique for reshaping data, you could say, to make it much more suitable for analysis.
And we're focusing specifically on one powerful method, the Box-Cox data transformation.
That's right. And, to really get a handle on this, we've looked at quite a range of material. There's the original seminal 1964 paper by Box-Cox themselves.
The foundational work.
Absolutely. But also practical stuff from statistical software manuals. Think NCSS, Minitab, ArcGIS Pro, and online resources, too. Our bloggers, Geeks for Geeks, SixSigma.us, places like that.
Even discussion forums like Reddit showing how it's used, well, in the real world by practitioners.
Exactly. It gives a broad picture.
So our mission today is pretty straightforward. Give you a clear, concise introduction to Box-Cox. We want to cover what it is, why you'd use it, and basically how it works without getting too bogged down in the, let's say, heavy mathematical machinery.
Just enough to grasp its value and function.
Precisely. So let's start right there. What exactly is the Box-Cox transformation?
Okay. So at its heart, it's a type of power transformation, named after the mathematicians George Box and David Cox, obviously.
Power transformation.
Yes. Its main goal, really, is to take data that isn't normally distributed, maybe it's skewed to one side or the spread isn't consistent, and mathematically nudge it so its shape is closer to that classic bell curve, the normal distribution.
Right, the Gaussian
distribution.
Yeah.
Why is getting data to look like that so important in stats and maths? What's the problem with non-normal data?
Well, a lot of statistical methods actually assume the data is normal. If it's not, you run into problems.
Like what kind of problems?
Things like relationships between variables appearing nonlinear when maybe there's an underlying linear link obscured by the distribution, or differing variances heteroacidicity, where the spread of the data changes across its range, and also just basic asymmetry or skewness. Box-Cox helps tackle these. So it's about making the data play nicely with common statistical tools by addressing those issues. You called it a power transformation. Can we look at the actual formula?
Sure. The general form for when the key parameter, lambda, that isn't 0, is y transformed equals y to the power of L minus 1, all divided by L.
Okay, y equals u1, where y is the original data.
Correct. That L, the exponent, is the crucial part. It controlled how the data is transformed.
That's the power. But you said when lambda isn't 0, what happens if lambda is 0? You can't divide by 0.
Ah, good point. That's a special case mathematically.
Yeah.
As lambda gets very, very close to 0, the transformation smoothly becomes the natural logarithm of y. So y ln y.
So taking the log is actually part of the same family of transformations.
Exactly. It fits right in. It's often a very useful transformation in its own right, especially if the data analysis suggests an optimal lambda very close to 0.
That's a neat mathematical link. So lambda determines the specific transformation. Are there common sort of landmark lambda values that correspond to familiar operations?
Yes, definitely. We can think of a few key ones. Lambda 1 is the easiest.
What does that do?
Nothing. It just leaves the data as it is. Y to the power of 1 is just y.
Okay, so up 1 means no transformation needed.
Right. Then 0.5 is the square root transformation, square root of y.
Okay.
Okia, as we just said, is the natural log, ln y.
Got it.
Ovoid 0.5 gives you 1 over the square root of y.
The inverse square root.
And Ogon 0.1 is the reciprocal, just 1 over y.
Right.
You could have others too, like Longothos 2 for squaring the data, y2.
Right.
Or Ogomis 2 for the inverse square, 1y2. It covers quite a range.
That really helps visualize the possibilities. Now, instead of just picking one of these, how do we figure out the best lambda for our specific data set? It's not guesswork, is it?
No, definitely not. This is where statistical software comes in. It uses a method called maximum likelihood estimation, or MLE.
MLE. How does that work in principle?
Well, essentially, the software tries out a whole range of lambda values, often between, say, -5 and 5, or maybe -2 and 2. And for each lambda, it transforms the data and then calculates how likely that transformed data is, assuming it came from a normal distribution. It picks a lambda that gives the highest likelihood.
So it's finding the lambda that makes the transformed data look most normal, statistically speaking.
Precisely. Often this boils down to finding the lambda that minimizes the standard deviation of the transformed data, or maximizes something called the log likelihood function. They're related concepts.
So it's quite an objective, data-driven process. I think some sources mentioned confidence intervals for this lambda.
Yes, that's important. The software usually provides a confidence interval, typically a 95% interval, around the best estimated lambda.
And what does that tell us?
It gives a range of plausible values for the true optimal lambda. A key practical tip, often highlighted, is to check if the value 1 falls within this interval.
Because lambda 1 means no transformation.
Exactly. If 1 is inside the confidence interval, it suggests that, statistically, you might not actually need a transformation. The original data might be close enough to normal, or the evidence for transformation isn't strong enough.
But if 1 is outside the interval,
Then it strongly suggests a transformation is beneficial for achieving normality. That's a very useful rule of thumb. What about rounding the lambda? I saw mention of simplifying it.
right, sometimes the mathematically optimal lambda might be, say, 0.43. For easier interpretation, software might suggest rounding it to the nearest simple transformation within the confidence interval.
Like 0.5, the square root, if that's plausible.
Exactly. Or if the optimal is, say, negative 0.9 and the confidence interval includes negative 1, you might just use negative 1, the reciprocal, because it's easier to explain and understand conceptually.
Makes sense. Okay, we've got the what and the how. Let's circle back to the fundamental why. Why is achieving this normality so crucial? Well, as we touched on, many standard statistical procedures, think t-tests, ANOVA, linear regression, process control charts, they are mathematically derived assuming the data, or the errors in a model, are normally distributed.
That's a core assumption.
It really is. If your data violates that assumption significantly, the results you get from those tests, well, they can be unreliable. P-values might be wrong, confidence intervals inaccurate, your conclusions could be misleading.
So Box-Cox is a pre-processing step to make the subsequent analyses valid and trustworthy. What are the main benefits we see after a successful transformation?
Several key things. It can often straighten out nonlinear relationships between variables, making them easier to model linearly.
Okay.
It stabilizes variance, that heteroscedasticity problem we mentioned, so the spread becomes more consistent.
Right.
It reduces skewness, making the distribution more symmetrical around the mean.
Which improves the overall fit to the normal curve.
Exactly. All these things make the data much more suitable for a huge range of standard statistical techniques.
It sounds incredibly useful. Are there specific fields where you see Box-Cox used a lot?
Oh yes, it's quite widespread. In manufacturing and quality control, for instance, it's used in process capability studies to ensure processes meet specifications, especially when the raw output data isn't normal.
I see.
In finance, it might be used to analyze market returns, which often aren't normally distributed. Environmental science uses it too, perhaps for modeling pollutant concentrations. The original paper itself had examples from textiles, biology.
Yeah.
It's versatile.
So, a broadly applicable mathematical tool. Now, are there any catches, any limitations or things we need to be careful about?
Yes, definitely. A major one is that the standard Box-Cox transformation we've discussed requires the input data to be strictly positive, greater than 0.
Why is that?
Well, look at the formula. You're raising y to the power of lambda. If y is 0 or negative, taking logarithms for or fractional powers like square roots for 0.5 becomes problematic mathematically.
Right. You can't take the log of 0 or a negative number or the square root of a negative number in standard real analysis. So what do you do if your data does have zeros or negatives?
A common workaround is to add a small positive constant to all the data points before applying the transformation. Just enough to shift everything above 0.
Does that distortion matter?
It can, slightly. You have to be mindful of it.
Yeah.
Alternatively, there are other transformation families, like the Yeo-Johnson transformation, which are designed from the ground up to handle 0 and negative values without needing that shift.
Good to know. There are alternatives. Any other caveats?
Another key thing, Box-Cox doesn't guarantee perfect normality. It aims to improve it, often substantially, but you should always check the transformed data afterwards.
How do you check?
Using statistical tests for normality, like the Shapiro-Wilk test, and also, very importantly, by looking at visual plots like histograms or normal probability plots, QQQ plots, of the transformed data.
So, verify. Don't just trust the transformation worked perfectly. What about things like sample size or outliers?
They matter. The precision of your lambda estimate, shown by the confidence interval width, depends on the sample size.
Yeah.
Smaller samples mean less certainty.
Makes sense.
And outliers can sometimes throw off the transformation. If you have really extreme values, Box-Cox might struggle to normalize the bulk of the data effectively. It's not a magic bullet for every data problem.
And sometimes a simpler approach might be better.
Yes, that's a point about interpretability. Even if Box-Cox suggests, say, lambda equals 0.18 is optimal, if a simple log transform, Lambda 0, does a reasonably good job and is easier to explain in the context of the problem. Some researchers might prefer the simpler log transform. It's a judgment call.
Balancing statistical optimality with practical understanding. This has been incredibly clear. So if we were to sum up the key takeaways.
I'd say the main message is that Box-Cox is a flexible, mathematically derived tool that helps morph data towards a normal distribution, and that normalization is often crucial for applying many standard statistical methods correctly.
And finding the right transformation involves that parameter lambda, estimated typically using maximum likelihood in software.
Exactly. But remember the limitations, the need for positive data in the standard form, and the fact that it doesn't always achieve perfect normality. Always check the results.
Use it thoughtfully. It's a powerful technique, but needs careful application and verification.
Couldn't have said it better.
This really highlights how manipulating data mathematically isn't just a technical step, is it?
Not at all. And it leads to a fascinating final thought, perhaps. When we transform data like this, we're essentially choosing to look at the phenomenon through a different mathematical lens. It lets us use our standard tools, yes, but does changing that perspective, shifting how we measure or scale things, reveal fundamentally new insights that were hidden in the original view?
What new patterns emerge when we warp the scale? A really provocative question to end on. Thank you for this enlightening discussion.
My pleasure.